Now let's move on to the third problem. This is a simplistic version of the Rankine cycle. Okay, and what we are told is we're dealing with 10 tons of municipal solid waste. So this is just solid biomass, right? And we are burning it directly in a boiler to generate saturated vapor at 200 degrees Celsius. You can imagine a TS diagram, right? And this is a simple Rankine cycle that we're looking for. Okay, so we have the TS diagram here, and we're looking for uh, the boiler exit to be saturated vapor at 200 degrees Celsius. So let's say this is the boiler exit, right? And let's call this state 2. It's saturated vapor and it's at 200 degrees Celsius. Two properties, so you can define the state. Now, water enters the boiler as a compressed liquid at 20 degrees Celsius. So, well, we can simply uh, draw the TS diagram. It's going to look something like this. It's a constant pressure heat addition. So, the water it enters the boiler at state 1, and the state 1 is 20 degrees Celsius. Now, of course, that it comes from a pump, so we can sort of assume something like an isotropic compression in the pump, let's say, and well, maybe I'll have to redraw this. Give me more space. All right, so this is state 2. This is state 1. So this is state 4, and yep, that's what we have information for now. Now we are told that the heating value of the municipal solid waste, this 10 of this municipal solid waste that we're using, 10 tons of which we have, is 18,000 kilojoule per kilogram. Okay, so 1 kilogram is going to produce 18,000 kilojoule. Where do we need that? Well, we need that from process 1 to 2, which is the heat addition within the boiler. Now, we are told that the boiler efficiency is 75%. So not all of the heat generated by burning that fuel will go to heating the go to converting the liquid water to steam. Only 75% of it will be used, right? Because of the inefficiency within the boiler. Now, first thing is we need to determine the amount of steam generated, right, within the boiler. So we're looking at the mass of steam generated, essentially. And we are told that we can assume the enthalpy of compressed liquid, which is state 1. State 1 is compressed liquid. We can assume this enthalpy of compressed liquid, state 1, to be equal to the enthalpy of saturated liquid, HF, at the same temperature. So we are basically told that we can take the assumption that H1 is almost equal to HF at 20 degrees Celsius. Now, this is a very reasonable assumption. It's not something new. This is standard practice and in thermodynamics. Okay, so the pressure when we are dealing with compressed liquid, the pressure doesn't have much of an effect. So we don't even have to know what pressure it is at. Now, we have this information. H1 is equal to the saturated liquid enthalpy at 20 degrees Celsius. And so from the tables, you can simply get HF at 20 degrees, which comes out to be 83.91 kilojoule per kilogram. So that's H1 already for us. Okay. Now, H2 here is simply Hg at 200 degrees Celsius because we are told that it was saturated vapor. So which means, again, looking at the table, we get H2, the value of H2 to be 2792 kilojoule per kilogram. Okay. Now, when we look at the boiler, the heat input within the boiler is equal to the mass of steam, right? Or the mass of water, both of which are exactly same, times the enthalpy change, right? Enthalpy change within the boiler, which is H2 minus H1. This is the enthalpy change within the boiler. And this exactly should be equal to the boiler efficiency times the mass of waste that we were burning, mass of municipal solid waste, times its heating value. Okay, so when you burn the waste, you get a certain amount of energy. 75% of that energy, because of boiler efficiency, is eventually converted to is eventually used for converting liquid water to steam, which is what shows up as QM, right? So here, basically, we have been provided with boiler efficiency, the mass, the heating value. H2 and H1 is what we have calculated or found from the tables based on the information given. So we can directly calculate mass of the steam, right? So mass of steam comes out to be boiler efficiency 0.75 or 75% times mass of municipal solid waste. 10 tons means 1 ton is 1,000 kilograms. So we're talking about 10,000 kilograms here, right? So this is simply mass of municipal solid waste is 10,000 multiplied by heating value 18,000 kilojoule per kilogram divided by S2 minus H1, right? And S2 is simply 2792 minus 83.9. Okay. So when we do the mass of the steam comes out to be 49,850 kilograms. So this is the amount of steam you can generate by burning 10,000 kilogram of municipal solid waste. Okay. So this is part one of the problem. Now, once you generate that steam, we are told that this generator steam is running through a turbine generator unit to produce electricity, of course. Yeah. So the steam that we have at state two, we let it expand within a turbine unit, and then the turbine unit is coupled to a generator, and it produces electricity. Now the steam pressure at turbine exit is 100 kilopascal. So uh, at state three, the pressure is 100 kilopascal. So P for state three is, which is always equal to P for state four, is 100 kilopascal. Okay. Now, if the turbine isentropic efficiency is 85%, which means that, okay, 2 to 3 is not an isentropic process. So isentropic efficiency for the turbine is 85%. The generator efficiency is 95%. We want to determine the amount of electricity produced, and we can neglect pump power input. So we simply have to determine the amount of power output in the turbine, right? So power output in the turbine, negligible pump power input. So power output in the turbine is the amount of electricity generated, the amount of work generated within the turbine. And then using generator efficiency, we can convert that into the amount of electrical energy generated. And once you do that, we want to produce, we also want to calculate the revenue generated. So first calculate electricity produced, and then how much revenue can you make from it if you sell the electricity at this given price. Okay, so let's then go ahead and look at the other part of the problem. So the mass of the steam has been calculated, right, as shown here. Now we are focusing on calculating the power output from the turbine, right? For calculating the power output for the turbine, we need information for state 2 and state 3. State 2, we have the information already, right? We don't have information on state 3. So, and also there's an isentropic efficiency. So this vertical line that I drew actually becomes 3s. The actual line is going to be somewhere like this, representing the actual state, okay? Irrespective of the isentropic efficiency, the pressure for 3A is always equal to the pressure at 3S. The only thing that's different is the enthalpy, right? And in some cases, the temperature as well. So now we have the isentropic efficiency given for the turbine. Isentropic efficiency is going to be equal to H2 minus H3 actual, the actual work output, divided by the isentropic work output, H2 minus H3S. So first thing is to find out 3S, right? And how do we find out 3S? Well, for isentropic expansion, for isentropic process, let's say 2 to 3, we know that S2 will be equal to S3S, right? And we also know that pressure at state 3, uh, whether it's actual or isentropic, it's given as 100 kilopascal. So by making use of the pressure and the entropy that is provided to us, we can calculate the enthalpy at state 3s. It comes out to be 2328.8 kilojoules per kilogram. Well, in case you have not noted down, S2 is going to be obtained from the state 2. We said that state 2 is saturated vapor at 200 degrees Celsius. So this is Sg at 200 degrees Celsius is basically S2, right? So once you have that, then you can calculate everything. From S2, you have S3, and we have the pressure. So at these conditions, the enthalpy comes out to be 2328.8, the isentropic one, right? So by you making use of this formula, so here in that formula, we can calculate S3A as H2 minus isentropic efficiency of the turbine times S2 minus S3S. Okay, so when you plug in all the numbers, the value of H3A should come out to be 2398.3 kilojoule per kilogram. So now we have S3A, we have S2 already, right? So with this, we can basically go ahead and start solving the rest of the problem, right? So S2 was 2792 kilojoule per kilogram. S3A or S3 is came out to be 2398.3 kilojoule per kilogram. Okay, and just again for reference, we're looking at Rankine cycle. This is state 2. Vertical line will give you 3S. This is 3A or 3 because of the increase in entropy, and then we end up with state 4 and 4 to 1. We are not considering 4 to 1 process, but 2 to 1 process or 1 to 2 process is considered in the boiler. 2 to 3 is the expansion part. Okay, we're not even looking at heat rejection. So now we have S2 and S3. You can calculate the work output from the turbine, okay, which is the net work output because we are neglecting the work output, work input in the pump. So this is mass of the steam times S3 minus S2. Mass of the steam we calculated by using the information given for the boiler, and it came out to be 49,850 kilograms. Okay, which means that here, when we calculate the work output, it's 49,850 times 2792 minus 2398.3. Okay, so this is the work output from the turbine, but we are not really interested in the work output in the turbine. We are interested in how much electrical energy is being generated from it, right? So electrical energy should not be a dot. Electrical energy generated from it is simply generator efficiency times the work output of the turbine, right? So work output of the turbine is mechanical work output. You have to convert it to electrical energy using the generator, right? So now the generator has an efficiency of 95%. So 0.95 times 49,850 times 2792 minus 2398.3. So you'll get the answer in terms of kilojoule. However, when we talk about the electricity price or electricity, we normally are talking about a different unit of energy, which is kilowatt hour. Okay, so we want to convert this available electrical energy. We want to write that in terms of kilowatt hour. So the way to convert kilojoule to kilowatt hour is to simply divide the amount in kilojoule. You divide it by 3,600. Okay, when you do that, then you get the electrical energy in kilowatt hour, and it comes out to be 5,180 kilowatt hour. Now, this is the amount of electrical energy being produced. Okay, now once you have it, then the revenue or how much money you can make out of it is simply the amount of energy you produced in kilowatt hour multiplied by the reals per kilowatt hour, right, for 1 unit. And this comes out to be 1,331 real, right? So all we had to do was go to follow the typical process for a Rankine cycle, and then once you calculated the work output, convert that into electrical energy using generator efficiency, and using that, then the next step was simply to convert the kilojoule to kilowatt hour, which we did by dividing by 3,600. And then once you know how many units of electricity you are producing, the revenue was calculated by multiplying this unit of these many units of electricity, or 5,180 units of electrical energy, by the price we get for each unit. So that's the end of this problem.